Hey guys, this is just an introduction to radioactivity and some of its basic concepts and equations. I will be making more videos on experiments in radioactivity and binding energy. First and foremost, I am only a student and these are some of the notes I made and used for studying. I hope you will find these notes as useful as they were for me. Isotopes. You have probably heard this term if you did O-level chemistry and even more so if you did A-level chemistry. The definition is basically the same. Atoms of the same element with the same atomic number but different mass number. Now, atomic number is the number of protons and mass number is the number of nucleons, that is, protons and neutrons. So in terms of subatomic particles, isotopes are atoms of the same element with the same number of protons but different number of neutrons. In this example, we have isotopes of hydrogen. Protium, deuterium, tritium all have the same number of protons, that is 1, but different number of neutrons. Protium having 0 neutrons, deuterium 1, and tritium 2. Stability of a nucleus. So a nucleus is said to be stable if it has the same number of protons and neutrons. If either of them, the number of protons or the number of neutrons, is more than the other, the nucleus is unstable. If a nucleus is unstable, it will undergo radioactive decay to become more stable. And what is radioactive decay exactly? An unstable parent nucleus decaying to a more stable daughter nucleus and some other particles, releasing ionizing radiation and energy. If the daughter nucleus is stable, the decay process stops. However, if the daughter nucleus is unstable, it keeps decaying until it becomes stable. This decay process is called a decay series. Radioactive decay has some properties. A. Random. You cannot predict when a particular nucleus will decay and which nucleus will decay next. And B. Spontaneous. It is not influenced by external factors, be it temperature, pressure, or even the behavior of the neighboring particles. So radioactive decay releases energy. M1 represents the mass of the parent nucleus and M2 mass of the decay products, that is the daughter nucleus and the other particle, example alpha particle. Always during radioactive decay, mass of the parent nucleus is greater than the mass of the decay products. And why is that? It is simply because some mass of the parent nucleus is converted into energy according to Einstein's E equals mc squared. This large amount of energy is released as kinetic energy of the decay products and some heat energy. However, in calculations, we assume that the total energy is released as the kinetic energy of the decay products. Now, what is delta M? It is basically the mass deficit. That is the difference in mass between the parent nucleus and the decay products. And energy release can be basically calculated using E equals mc squared. So, we can say that this mass deficit has equivalent amount of energy and is the total kinetic energy of Y and Z. Momentum and kinetic energy. Initially, the parent nucleus is at rest because this is a decaying process and not a collision. So, the nucleus is not moving. So, momentum before decay is 0. Since momentum is conserved because there are no external forces acting, total momentum after decay should also be 0. So after decay, both the daughter nucleus and the other particle, example alpha in this case, are moving. So they should have the same magnitude of momentum in the opposite directions. So they must be moving in opposite directions, right? And now how do we know which decay product is moving at a higher speed? It's pretty simple. Using the equation momentum equals mass into velocity. We know momentum is the same. So we can say velocity is inversely proportional to m, and since electron is much lighter compared to the daughter nucleus, electron moves at a much higher speed. So basically, the lighter decay product moves at a higher speed. Similarly, how do we know which decay product has higher kinetic energy? Using kinetic energy equals momentum squared over 2m. So we know momentum is the same. So the lighter decay product will have much higher kinetic energy. Like I said before, the energy released is released as the kinetic energy of the decay products. So this makes sense. Now we come to the types of decay. We have alpha decay, beta minus, beta plus, and gamma emission. Now alpha decay is basically an unstable parent nucleus decaying into a more stable daughter nucleus by emitting an alpha particle and energy, and beta minus is a neutron in the unstable parent nucleus splitting into a proton and electron. Neutron is replaced by proton and electron is ejected at high speed from the nucleus as beta minus. And beta plus is a proton in the unstable parent nucleus splits into a neutron and positron. The proton is replaced by neutron and positron is ejected at high speed from the nucleus as beta plus. And what is gamma emission? When alpha or beta decay takes place, nucleus will be in excited state and will have surplus energy. When the nucleus returns to the ground state, surplus energy will be emitted in the form of gamma photons. Now, these are the general equations of these decays. And as you can see, you must know the atomic number and mass number of alpha particle, beta minus, and beta plus. It's very important because they give questions where you have to complete the atomic number and mass number of Y and alpha or beta. So if you know the atomic and mass number of alpha, beta minus, and beta plus, you can complete Y because they have to be balanced, the atomic numbers and the mass numbers. Then we have conservation properties. In alpha decay, all properties are conserved. That is total mass, energy, charge, momentum, baryon number, lepton number, and strangeness. However, in beta minus and beta plus decay, strangeness may not be conserved or may be because it occurs through weak interaction. However, the others, total mass, energy, charge, momentum, baryon number, lepton number, must be conserved. Another thing to note is that in beta minus and beta plus decay, a nucleon, that is in beta minus a neutron, is replaced by a proton. So a nucleon replacing a nucleon, right? So the nucleon number remains the same. That's why you don't see the mass number changing in either of them. Then we come to properties of alpha, beta, and gamma. So alpha, like I said before, helium nucleus and has the notation alpha mass number 4 and atomic number 2. Beta has mass number 0 and atomic number -1 and is a fast moving electron. Gamma is high frequency, high energy electromagnetic radiation, so has notation as this and has no charge, right? And yeah, so now when we come to relative charge, if you remember from unit 4, the atomic number represents the charge, right? And the mass number represents the baryon number. Okay, and now the actual charge, basically this is plus 2e minus 1e, and e represents electronic charge, which is 1.6 into 10 to the power minus 90. So when it comes to charge, you have to multiply, when in calculations, if to know the charge of an alpha particle, you have to multiply plus 2 into 1.6 into 10 to the power minus 90, which is 3.2 into 10 to the power minus 90. Likewise for beta. Then we come to ionizing ability. Now, what is ionization? Basically, removing an electron completely from an atom, right? Alpha has the highest ionization and gamma negligible. And beta plus cannot ionize simply because it annihilates with electrons. Then we come to penetrating ability. It's very weak for alpha and highest for gamma. Range in air. Now, what is range? The maximum distance a particle can travel through a medium. So alpha particle has the lowest and gamma has infinite, right? And as you can see, there's this unsaid relationship between ionizing ability and range in air. The particle which has highest ionization ability will have the lowest range, right? Why? Answer is pretty simple. It's because when ionizing ability is high, it interacts with particles more frequently, and as it loses a small amount of energy at each ionization, energy will be lost rapidly and is stopped rapidly, therefore range will be lower, right? Then this is how we can stop the materials: a sheet of paper, thin sheet of aluminum, and lead. Background radiation, basically radiation around us in the atmosphere. It can be naturally existing elements and man-made elements. For example, food and drinks, example like sausages, dead and living plants and animals, uranium deposit in soil, radioactive rocks, example granite. For background radiation, in another video, I will be explaining how to measure background radiation and how to use it and why it's important to consider background radiation. Activity denoted by A and is defined as the number of nuclei decayed per second. Lambda is the decay constant and indicates the probability of decay at any given instant. Since it's a probability, it should always be less than 1. So, yeah. And when we use this equation, it is very, very important that you use lambda in per second. The unit of lambda should be per second, because activity's unit, SI unit is becquerel. However, its base unit is per second. So whenever you use this equation, you must use lambda in per second. You must not per year or per minute, it should be per second. And the negative sign shows the number of radioactive nucleus present decreases with time. And since lambda is a constant for a particular radioactive element, we can say that activity is directly proportional to number of radioactive nucleus present. Okay. Now, when a radioactive element decays, number of radioactive nuclei present in sample, activity of the sample, and mass of the sample decreases exponentially. So the equation is, now whenever you use these equations, you must make sure the unit of lambda and time should be the same. That is, if you find lambda in per second, time should be in seconds. If it's in per year, then this should be in years, because only then they will get cancelled. Yeah. Then we have this equation: rate of energy release equals activity into energy per decay. Now, what is rate of energy released? It is basically power. Power is equal to activity into energy per decay. How do you know energy per decay? E equals delta mc squared, right? So that gives us the power. This equation is not there in textbooks, but I figured this equation out because it was there in one of the past papers. So I think this equation is quite important. Half-life. Okay, so if you've done capacitors, it's almost a very similar definition. The average time taken for activity or the number of nuclei present in the sample or count rate to drop to half of its initial value. And like lambda, that is the decay constant, half-life will be constant for a particular type of radioactive element. Now this is the derivation of the equation for half-life. So, hope you can go through it. When T is T half, that is T half, N will be half of the initial. So when we substitute, N naughts get cancelled, and when we simplify, we get this. And we take ln on both sides and make T half the subject. And we derive this equation. Now we have the graph for number of nuclei number of nuclei in the sample against time and activity against time. So both of them follow an exponential decay, exponential graph. Now what I mean by the term exponential graph is this. A0 over A1 is equal to A1 over A2 plus A2 over A3. Now I'm going to tell you what A1 is. If I take equal time intervals, so let's say this is T, and similarly this is 2T, and this is 3T. Okay, so the time interval is basically time T, right? Equal time intervals. And this is A1, A2, and this is A3. Now what I mean by exponential decay is at equal time intervals, the ratio of A0 and A1 will be equal to the ratio of A1 over A2, equal to the ratio of A2 and A3 over A3, if the graph follows an exponential decay. Similarly, N0, if I do the same thing for N0, it will be the same. N0 over N1 equals N1. So that's how we show a graph follows exponential decay, right? And another thing I would want you to notice is, if they give a graph and expect you to find the decay constant, you can simply find half-life of the graph by taking half of the initial value and then you drop a line and you find half-life, right? So that's your T half. Now we know T half is equal to ln2 over lambda. So lambda is ln2 over T half. So that's how you find decay constant. And if I want to convert this graph into a straight line graph, into y equals mx plus c graph, this is how I do it. I take ln on both sides of the equation. So ln a is equal to minus lambda t plus ln a naught. I get this equation. And I plot a graph of ln a against t, as you can see. And I'll get a straight line graph with a negative gradient, which is minus lambda. And my y-intercept will be ln a naught. Okay. Yes. Now we come to carbon dating. Basically, what is carbon dating? It is basically a method to find age of a biological specimen. And it simply works by comparing the two isotopes carbon-12 and carbon-14. So carbon-14 is a radioactive element, whereas carbon-12 is a stable element. And plants take carbon-14 as carbon dioxide during photosynthesis. And from plants, all animals, all living organisms get C14, carbon-14. So when a person is living, the ratio of C14 to C12 is constant. However, after their death, the ratio of the amount of C14 will decrease exponentially, causing the ratio of C14 to also decrease, C14 to C12 to also decrease exponentially. So using this exponential decay, we can find age, that is the duration from its death. So how we do it is, we find the ratio of the sample in the archaeological site. Then, let's say a bone. We find a bone in archaeological. We find the ratio of C14 to C12 in that bone. Then we find the ratio of a bone in a the ratio of C14 to C12 in a currently living sample. in a currently living sample of a bone. And we assume that the initial ratio when it was living was the same ratio as this currently living sample, right? And we assume this is R naught. And then we can use this equation, exponential equation. But the problem with this method is the environmental conditions when this bone was actually living was probably different. So the ratio of C4 into C12 probably was different. So that's where the error comes into play, right? Because of the different environmental conditions like temperature and pressure, right? Okay, so that's it, and I hope you found this video useful, and thank you for watching.